Metallography Part 2 Microscopic Techniques. Metallic materials are widely used in many areas of everyday life. How are they built up internally? Are there perhaps crystals to be found? And if so, how big are they? What kinds of crystals are there? What is their shape? And are there voids or inclusions? Metallography gives an answer. In this video, we would like to introduce the microscopic techniques of metallography. Microscopic means to investigate a workpiece at higher magnification, usually with a light microscope. To have a look at the inside, the material has to be prepared properly, and this is how it is done. First of all, a small specimen has to be cut from the actual workpiece. The specimen is mounted in resin, ground in several stages, polished in several stages, and finally etched. Now the specimen is completely prepared and ready for microscopy. As a typical example, we are going to investigate a bar made from a steel used millions of times, the plain carbon steel C45E, with 0.45% of carbon. To start with, one of our material testers defines the intended sectional plane and marks it on the bar. In this case, it's a longitudinal section. Then he takes the bar to the abrasive saw to cut out a small sample. He fixes the bar securely, prepares the machine, selects the cutting parameters, and starts the first abrasive cut. Intensive water cooling and appropriate cutting parameters are important to keep the material as cool as possible. After finishing all abrasive cuts, the material tester picks up the sample and hands it over to his colleague. For further processing, the specimen has to be mounted in resin. To ensure that the resin will adhere well to the specimen surface, the specimen is placed in an ultrasonic cleaner bath for a few seconds. Alcohol and ultrasonic waves help to remove fat and loose particles from the surface. A short time under the hairdryer and the specimen is clean and dry. To mount the specimen, small plastic molds are suitable. The material tester picks up the clean specimen and carefully places it into one of the molds. The intended plane of examination is at the bottom. Then he pours liquid resin into the mold. A thin layer of grease at the inner surface of the mold acts as a release agent. This ensures that the cured resin can later be released easily from the mold. Now the mold containing the specimen goes into the light curing unit. Under the action of intense blue light, the resin polymerizes within half an hour. The resin has cured and embedded the specimen well. As an alternative to light-curing resins, many other embedding materials are available. Each of them has its own advantages and disadvantages. Because the top surface is still uneven and slightly sticky, the material tester grinds it there until it is even. He uses a rotating water-lubricated disc equipped with coarse-grained silicon carbide paper. The circumferential surface is slightly ground as well to ensure a clean specimen. Now comes the most important part, the preparation of the intended plane of examination. Our material tester begins with comparatively coarse 180 grit abrasive paper. He makes sure to press the specimen calmly and evenly onto the abrasive paper, compensating the tendency for the sample to tilt. He also makes sure not to grind his fingertips accidentally. Now he has achieved an even, relatively rough surface. The specimen is ready for the next step with finer paper. He inserts a new 320 grit abrasive paper onto the disc. Rotating the specimen by 90 degrees leads to new grinding grooves perpendicular to the old ones. In this way, the material tester can easily check whether the old grinding grooves have been removed completely. It is important to use sufficient water flushing during grinding. This keeps the sample cool and prevents the abrasive paper from being loaded with material particles. Grinding continues with 600 grit and 1000 grit abrasive paper until an immaculate, finely ground specimen has been achieved. The specimen is now ready for polishing. An absolute prerequisite for polishing is a thoroughly clean specimen. The ultrasonic bath and running water help to remove any residue from the ground surface. Otherwise, hard particles might be pressed into the polishing cloth and scratch the surface. Hands should be washed as well, so that no unwanted particles find their way to the sample and the polishing cloth. Now the material tester can start with a first polishing operation. He chooses a polishing disc equipped with hard cloth of low resilience, moistens the cloth with a suitable lubricant, and adds 2 splashes of diamond suspension of particle size 6 micrometers. Under counter-rotating motion, he presses the specimen with high pressure onto the polishing cloth. The diamond particles have settled on the cloth and are now abrading the surface. After about a minute, all grinding grooves have been removed and the specimen surface already has a shiny appearance. But still there are many fine scratches to be found, resulting from the 6 micrometer diamond abrasive. To remove them, the material tester washes the specimen and his hands again very carefully and polishes the specimen for a second time. Now he uses a softer short nap polishing pad, finer diamond suspension of 3 micrometer particle size and less pressure. After the second polishing operation, the specimen surface has an almost mirror-like appearance. No more scratches can be seen with the naked eye. Nevertheless, the specimen has to be cleaned again and go through a third and final polishing operation. This time, 50 nanometer aluminium oxide abrasive is used. Only then is the surface prepared to a sufficient quality. At the end of the mechanical preparation, special care has to be taken to clean the specimen properly. On the one hand, all abrasive particles have to be removed. On the other hand, the freshly polished surface must not be scratched or damaged. Under running water, the material tester gently wipes the specimen with cotton wool, thoroughly rinses it with alcohol, and dries it with a hairdryer. From now on, the sample is called a metallographic specimen or microsection. Judged with a naked eye, our metallographic specimen seems to be well prepared. It is now allowed to go under the microscope for the first time, or rather onto the microscope. In fact, the design of typical metallographic microscopes is inverted. Inverted means upside down. The microscope objective is not facing downwards as usual, but upwards. This offers the advantage of simply placing the metallographic specimen on top of the microscope stage. The prepared surface faces downwards. Using the built-in digital camera, the polished specimen surface can be observed on the computer monitor. In the polished state, there isn't much to be seen in this material. Only some elongated non-metallic inclusions can be observed, but if these inclusions are of special interest, then the polished state is the perfect one. Inclusions may best be seen here. However, if one wants to see the crystals, the grains and grain boundaries, then the microsection has to be etched. To do this, our material tester protects himself with a lab coat, puts on safety glasses and pours the etchant into a small glass bowl. The etchant consists of a solution of 10% of concentrated nitric acid in alcohol. Now he turns on the water tap, picks up the freshly polished microsection with gripping tongs and immerses it for a few seconds into the etchant. Then he rinses the microsection thoroughly with water and afterwards with alcohol. The hairdryer is again used for drying. The excitement increases. Was the etching time correct? Has everything worked out fine? At low magnification, not much can be seen, which looks characteristic. The tester gradually switches over to higher magnification. In between, he focuses and adjusts the brightness. At medium magnification, light and dark areas become visible. At comparatively high magnification, in some of the dark areas, fine stripes may be recognized. The microstructure in the darker striped regions is termed pearlite. Pearlite consists of thin alternating crystals of ferrite and cementite. The white regions are ferrite crystals. They consist of almost pure iron. Great! The etching has been successful. In a similar manner, virtually all materials of our world may be examined. This is the plain carbon steel C80 with 0.8% of carbon. Only pearlitic regions with their characteristic alternating layers of ferrite and cementite can be seen. And this is the plain carbon steel S235 after a color etching. It only has a low carbon content. The relative amount of differently colored ferrite crystals is high, the proportion of pearlite regions low. The variety of materials is huge, and each material needs its own individual preparation method in metallography. The preparation is often not conducted by hand as shown here, but by automatic methods. This saves time and money. The principle, however, is always the same: sectioning, mounting, grinding, polishing, and etching.